Hello everyone, and welcome back to the second video on lattice-basis reduction. In today's video, I'll present Gauss's reduction, also known as Gauss's algorithm. This is a classical algorithm for solving the shortest vector problem in integer lattices of dimension 2. The LLL algorithm, which produces a short basis in integer lattices of arbitrary dimensions, can be viewed as a natural generalization of Gauss's algorithm. Let me recall some terminology from the previous video on the mathematics of lattices. The double vertical bars represent the Euclidean length of a vector in n-dimensional real space. Lambda 1 of L, the first successive minimum, is the length of a shortest non-zero vector in the lattice L. Lambda 2 of L, the second successive minimum, is the smallest r, for which the lattice L contains two linearly independent vectors, each of which has length at most r. The problem we'll focus on is the following. Given a basis for a two-dimensional integer lattice L, find a smallest basis of L. By a smallest basis, I mean a basis u primed v primed, where the length of u primed is lambda 1 of L, and the length of v primed is lambda 2 of L.
A key idea for both Gauss's algorithm and the LLL algorithm is the notion of projecting a vector onto a subspace. In this video, we'll look at the simplest case, projecting one vector onto another, more precisely, onto the one-dimensional subspace spanned by that vector.
Let u and v be two non-zero vectors in two-dimensional real space, and suppose that they are not scalar multiples of each other. Our goal is to determine the projection of v onto the line spanned by u, as well as the projection of v onto the orthogonal line. To do this, let w be a non-zero vector orthogonal to u. That is, the dot product of u and v is 0. Then u and w are linearly independent, and together they form an orthogonal basis for R2. We can now express v as a linear combination of these two basis vectors u and w. The dot product of u and v is mu times the length of u squared. So the coefficient mu is the dot product of u and v divided by the squared length of u. Furthermore, u and v minus mu times u are orthogonal to each other. Therefore, the projection of v onto the subspace generated by u is mu times u. And the projection of v onto the orthogonal line is v minus mu times u. Gauss described his reduction algorithm in 1801. Interestingly, the algorithm was first discovered by Lagrange in 1773, but today it's usually referred to as Gauss's algorithm. The input to the algorithm is a pair of vectors u and v that form a basis for a two-dimensional integer lattice. We'll assume that v is at least as long as u. The first step is to compute the real number mu, such that mu times u is a projection of v onto the line spanned by u. Then, the difference v minus mu times u is a projection of v onto the orthogonal line. Notice that mu is a real number, but not necessarily an integer. If it happens that mu is an integer, then v minus mu times u belongs to the lattice. In this case, we could replace v by v minus mu times u. This would give us a new lattice basis, where the basis vectors are orthogonal to each other and shorter than the original basis vectors. Unfortunately, in general, mu will not be an integer, so v minus mu times u won't belong to the lattice. To handle this case, we'll take the closest integer c to mu, where ties are broken by rounding towards 0. For instance, the closest integer to 3.5 is 3, and the closest integer to minus 3.5 is minus 3. Since u is an integer, v minus c times u is guaranteed to be in the lattice. And u and v minus cu is a basis for L. Typically, this basis is shorter than the original basis, since V minus Cu is usually shorter than V. Moreover, the two basis vectors u and V minus Cu are now closer to being orthogonal. Gauss's algorithm works as follows. The input is a basis uv for a two-dimensional integer lattice L. The algorithm outputs a new basis u primed v primed for L, where u primed is the shortest non-zero lattice vector, and the second basis vector v primed has length lambda2 of L, the second successive minimum. The algorithm repeatedly computes the real number mu, rounds mu to its nearest integer c, and replaces v with v minus cu. Notice that the new vector v minus cu lies close to the projection of v onto the line orthogonal to u. If necessary, u and v are swapped, so that u is always the shorter of the two. This procedure is repeated until c equals 0, which happens when the absolute value of mu is at most 1/2. It's not hard to verify that the output of Gauss's algorithm is indeed a basis for the lattice L. It takes more work to prove that the algorithm always terminates and does so efficiently. Indeed, it has been proven that the number of iterations in Gauss's algorithm is on the order of log x, where x is the length of the longer input vector v. Moreover, one can prove that all the integers involved in the algorithm are bounded by x. From this, it follows that the overall running time of Gauss's algorithm is big O of log x cubed bit operations. In other words, Gauss's algorithm runs in polynomial time. I won't prove these claims in this video. Let's walk through an example of Gauss's algorithm. We're given a basis u, which is 3, 5, and v, which is 4, 7, for a two-dimensional integer lattice L. The table shows the squared lengths of u and v, the real number mu, and its closest integer c, and the new basis vector v minus cu. In the first step, the new vector is 1, 2. This vector replaces v, and since it's shorter than u, we swap it with u. In the second iteration, the next new basis vector is v minus cu, which is 0, minus 1. Again, it replaces v, and since it's shorter than u, we swap. In the third iteration, the next new basis vector is 1, 0, which has the same length as u. Finally, c is 0, so the algorithm terminates. The output is a short basis u primed, which is 0, minus 1, and v primed, which is 1, 0.
Here is a second example of Gauss's algorithm, this time with longer vectors. You can follow the steps to confirm your understanding of how the algorithm works.
Next, I'll prove that Gauss's algorithm really does produce a shortest possible lattice basis. First, I'll show that the first basis vector u is a non-zero lattice vector of minimum length. Take any non-zero lattice vector w and write w as an integer linear combination of the basis vectors u and v. Now, the squared length of w is the dot product of au plus bv with itself, which can be written like this. We derive an inequality by replacing 2 times ab by minus 2 times the absolute value of a times b, and by replacing the last v with u. Now, recall the key termination condition in Gauss's algorithm that mu is at most 1/2 an absolute value. This implies that 2 times the dot product of u and v is at most the squared length of u. Substituting this back into our inequality and simplifying, we obtain this expression, which you can verify is at least the squared length of u. So we've established that every non-zero lattice vector w has length at least as large as U. Thus, U is indeed a shortest non-zero lattice vector. Next, I'll prove that the length of the second basis vector V is equal to the second successive minimum. Take any lattice vector W that is not a multiple of U. We can write W as an integer linear combination of the basis vectors U and V, where B is non-zero since W is not a multiple of U. Now, the squared length of W can be expressed like this. Next, add and subtract B squared times the squared length of U. Using the key termination condition in Gauss's algorithm, we derive this inequality by replacing 2 times the dot product of U and V with the squared length of U. We then replace A squared minus A times B plus B squared by 1 and add and subtract the squared length of V. Lastly, we simplify to obtain the squared length of V. This establishes that every lattice vector W not parallel to U has length at least that of V. Finally, consider any two linearly independent lattice vectors U primed and V primed. Since U primed and V primed are linearly independent, they can't both be multiples of U. Without loss of generality, suppose that V primed is not a multiple of U. Then V primed has length at least as large as V, by the argument above. Now, if U primed is a multiple of U, then its length is at least that of U. Otherwise, its length is at least that of V, again by the previous argument. In either case, at least one of U primed and V primed is at least as long as V. And this proves the result. We'll say that a basis UV for a two-dimensional lattice L is reduced if the parameter mu has absolute value at most 1/2. Gauss's algorithm always produces such a reduced basis for a lattice L. Moreover, as we've proven, this basis is in fact a shortest possible basis for L. This notion of a reduced basis extends naturally to higher dimensional lattices. However, a reduced lattice basis in n dimensions is not guaranteed to be short. To address this, we'll use a stronger notion of reduced lattice basis introduced by Lovász. As it turns out, the vectors in such a basis are relatively short, and the celebrated LLL algorithm efficiently computes one.
We'll present the LLL algorithm in video V4, after reviewing some background material from linear algebra in video V3.